Okay, great. So we have the final talk in the session by Minh Tran from currently IBM. He's going to talk about Hamiltonian simulation, the Magnus expansion. So.
Yeah, so I'm also going to talk about Magnus expansion today. And this is a joint work with Kunal Sharma, who's also in the audience. I'm very hungry, so I'm going to go quick. Please stop me if you have any questions, though. I'm really hungry. Yeah, I'm going to skip motivation. Yeah, right. So basically, we study Hamiltonian simulation. If you have a time-independent Hamiltonian, then what you are interested in is the state of some system at some later time. And for time-independent Hamiltonian, it's just simple time exponential. But for time-dependent Hamiltonian, you're going to have a time order exponential, and that complicates things when you're doing Hamiltonian simulations. So more precisely, usually we are given a description of a Hamiltonian. Let's say it's a sum of some Paulis, for example. You are given what is the time that you want to simulate, and you want to simulate the time dynamics of this system. So for example, here you only have a time-independent Hamiltonian, so that's very easy. Or like not easy, but we know how to do it. And usually you also specify what is the error of the simulation so that you will allocate the resource accordingly. And for the purpose of this talk, we will talk about mostly geometrically local Hamiltonian. And by geometrically local Hamiltonian, I mean a Hamiltonian that is supported on some lattice, where every terms of the Hamiltonian is only supported on qubits that are neighboring each other. For example, you can consider this nearest neighbor Ising model. And the common way to do it, at least on near-term device, and actually for even fault-tolerant device, is sometimes it's even better to just use shorter approximation. You are probably familiar with the first-order approximation, where you just, instead of evolving under the Hamiltonian, you approximate it by evolution under each term of the Hamiltonian. The second-order shorter is a little bit more complicated, where you go forward. So you implement the evolution under each term, and then you go backward in the reverse order. And you can generalize this construction to higher order shorter approximation. The benefit of going with higher order shorter approximation is that the error is now of higher order in time. And the error of shorter, as Defang has already mentioned, for first order shorter, the error is just the commutator between the terms of the Hamiltonian. And for higher order, the shorter error is just the nested commutator between the terms of the Hamiltonian. Now, that was for a small time. How do we go for larger time? For larger time, you just simply divide into many shorter steps. And in every shorter step, you apply the shorter approximation. So for example, in the first order approximation, the error will be second order. So it's t squared over r squared, where r is the number of shorter steps. And you multiply that error of one shorter step by the number of shorter steps. You get t squared over r. And now you can choose the number of shorter steps accordingly, according to the error of the approximation that you want. Right, so the object that we are studying today is the Hamiltonian that has multiple scale, or at least in this case, two scale, where you have a Hamiltonian that is A plus alpha B, where A is some Hamiltonian that is easy to simulate, and B is some Hamiltonian that is more complicated, but is the source of why we want to study this Hamiltonian. Like for example, you can consider A as some local Hamiltonian, like single site Hamiltonian that is totally not interesting. But B is something that gives this Hamiltonian some interaction. So the idea here is that if alpha is small, you would want to spend less time on simulating A, because A is boring. You want to simulate B. B is interesting. But because if you're using trotter, you are basically allocate the same amount of time on simulating A and simulating B. So is there a better way of simulating this Hamiltonian of A plus alpha B for some small alpha? So the natural idea when you have this kind of Hamiltonian is to move into the interaction picture of A. So now you end up with just a simple exponential of A, and then some time order exponential of B. And as the other speakers earlier today also mentioned, the reason like this time order exponential suddenly become way more complicated to implement. But the intuition here is that for local Hamiltonian and for a small time step, the exponential, the time order exponential here can actually be implemented pretty easily. So the idea is to use the Magnus expansion. You approximate, or you can exactly write the time order exponential as a simple exponential of some operator omega, where omega you can expand in different order of time. And the first order in omega is just a simple integral of this operator B. And the second order is some nested commutators between the B and itself at different times. Now the main idea for our algorithm is to just write this time order exponential in the interaction picture in terms of Magnus expansion, and then truncate the Magnus expansion. And then to implement the evolution under the truncated Magnus expansion, we just estimate the Magnus, we just evaluate the Magnus operator classically. The reason why we can do it classically is because, again, the Hamiltonian that we consider is geometrically local. So by the Lieb-Robinson bound, it guarantees that the Hamiltonian in the interaction picture is also approximately geometrically local. And the locality of the Hamiltonian in the interaction picture is guaranteed to be small because the time that we're considering is small. So we are only working in one time step at this point. For example, if we are using first order, like keep only the first order Magnus expansion, then the arrow will be alpha squared t squared n. And that's the same alpha squared that Raul mentioned earlier. If you were to use trotter, for example, then you wouldn't get this alpha square. You would get alpha because that comes from A as well. Right, so just a simple numerical example to convince ourselves. We consider this Hamiltonian where A is just simply a single side term and B is some random XY model. And we're gonna do some simulation of what is a trotter arrow in the one time step. And you can see here that the green and the red one, they are first and second order approximation. Both of them grow linearly with alpha, where alpha, remember alpha is a small constant in front of B. But the Magnus expansion, it grows as alpha squared. That's what we expected. So for to analyze the performance of this algorithm, we will have to understand what are the source of the error in this approximation. One error is the error in truncating the Magnus expansion. The other error is another error is the error in, remember, like after we truncate, we have this omega 1, omega 2, and so on. But omega 1, omega 2, and so on, they are let's say omega 1, they are the Hamiltonian of the perturbation B evolved under A. So they can be very non-local. But because of the Lieb-Robinson bound, you can actually truncate that time evolved operator to some Lacan that is controlled by the time of the size of the time step. And then after we do that truncation, we just calculate the Pauli decomposition of the Magnus expansion. After we compute this Pauli decomposition. Now we're gonna just use regular Trotter approximation to approximate this error. So we're gonna have three different sources of error here. So for the first one, that's one of the main technical results of this paper is to show that after you truncate to, let's say, P order, or here Q order, then the error of the approximation will be, the only thing that you should worry about here is the dependence on alpha and n. So on the dependence on alpha will be just alpha to the Q plus 1. Remember earlier, if you take only the first order, that means Q equal to 1, then the dependence will be alpha squared. And the second thing that you want to pay attention to is the dependence on n, the system size. Remember, like when you truncating the other terms, you have nested commutators between the terms of the Hamiltonian. And normally, if you don't have locality, then the nested commutator will scale as n to the q plus 1. That basically you just take the norm of the Hamiltonians and raise to that to the power, to the number of nested layers. But because of locality, it's only n here. Oh yeah, so I also mentioned there that without locality is n to the q plus 1. Yeah.
Quick question here. With your forming all of these commutations,
Yeah.
would normally stop me from complexity of the Magnus expansion order because the exponential.
Yeah.
Stop me from really going beyond q equals 4.
Yeah.
Can you
So yeah, so that's the thing. Like the key in your question is practically. So the number of Pauli's term here does grow exponentially with q, but like with n and t, that's efficient. So yeah, so in practice, I don't expect it to be able to go like beyond, I don't know, even the second order is going to be pretty difficult. Yeah. Yeah. So again, like here we're looking at the asymptotic scaling of this algorithm compared to other method for simulating either time-dependent Hamiltonian or Hamiltonian of this form where you move into the interaction picture. So again, with product formula, if you use higher order product formula, then the dependence on alpha is basically nothing. So you just have dependence on the system size and time. And the same goes, so for other algorithms, it's difficult to go to higher order dependence on alpha. And at the same time, if you look at the dependence on the system size, it also increases faster than linearly with the dependence on the system size. So for this paper, we have almost linear dependence on both alpha, n, and t in terms of the gate count. There's some nt to the gamma, where gamma is some constant that depends on the range of the Hamiltonian. Remember, we are considering geometrically local Hamiltonian, and gamma will depend on the range of that geometrically local Hamiltonian. And it can be, depending on the Hamiltonian, it can be at most a constant, but it can also be 0. If you consider the Hamiltonian that is just, let's say A is some local terms, or it has some special geometry that basically limit the number of Paulis in the decomposition. And again, as you've seen from this morning, there's quite a few papers that are working in this direction recently. And just to summarize, we consider a structure Hamiltonian that has this special form where you have A plus alpha B, where alpha is some small constant. And we show that there's a way to do the Hamiltonian simulation of this algorithm that is sometimes even better than using Trotter for near term and long term, in the sense that the scaling is better than Trotter, but it's also very friendly for near term devices. And it's better than post-Trotter, mostly in the sense that you can easily implement this algorithm without using any ancillaries. So that's basically the end of my talk. Again, the main level idea, if you want to take away from this talk, is that you just you just move into the interaction picture, expand the time order exponential in the Magnus expansion, truncate the Magnus expansion, evaluate the Magnus expansion classically, and then use trotter to approximate that Magnus expansion evolution. And thank you for your attention.
Okay, thank you. It's right on time, so we have time for questions. Throw it over there.
Yeah, right. I'm not good at. Thanks a lot. Maybe a naive question. So how does this compare with just doing Schrieffer-Wolf, like for your specific example?
Schrieffer-Wolf?
If I'm assuming like you're starting from like a time-independent term of A and B, and if I attempt to do Schrieffer-Wolf, and also kind of following up to the comment that you cannot go to much higher order in Q anyways, so.
Yeah, I haven't thought about that. I'm very hungry at the moment. So.
Fair enough.
Yeah, thanks for the question.
Yeah, thanks.
Questions not related to lunch, I guess. Okay, let's thank the speaker again.